Good morning. Thank you for, I'm delighted to be in Dresden again, and I'm quite honored that Falk and the program committee invited me to speak this morning to you for the first session of the day. Like Falk said, I work on serverless at Oracle, so I'm the director of product management for serverless, and I am involved in the FN project, which I'll talk about a bit, where we're doing serverless. So I'm going to talk to you about the challenges of using Java in the serverless environment. So serverless is kind of hot, and I'll talk about hot, how hot it is. And the challenges Java has, and then some of the things that we're seeing have been done and are being done to overcome some of the challenges of this environment. It's a bit of a different environment for Java than traditionally the Java or the JVM, for example, has been focused on. So I do work for a large company who requests that you do not make buying decisions based on something I might say. So I'll talk about future things. So serverless is not one thing. The first thing, the name is actually a bad name. It's not one thing. It's a whole bunch of things. Anything that is a service you're using where you're not provisioning the infrastructure yourself. So you're not provisioning virtual machines. You're not deploying applications to those VMs. You're not upgrading the operating system regularly. All that kind of management that you have to do is not serverless, right? So in serverless world, you deploy your applications, and some magical cloud pixie dust happens, and the servers appear behind the scenes, and they run for you, right? This is the advantage. A FAS, or a functions as a service platform, is essentially the compute component of a serverless platform. So if you go to a cloud provider who has serverless, they'll have network, they'll have storage, they'll have compute. Functions, or FAS, is the compute component. So I'm going to focus on the compute component here, FAS. So first off, what's a function? So a function is really just in Java, it's almost like a method, right? It's a simple single unit of work, or single unit of compute. It has input, it has output, it probably has side effects, so it may talk to a database, it may put something in storage, it might send an email, but this piece of code has one entry point. This is the key point, right? It has one endpoint. So if you're used to building microservices using, say, Spring Boot or something, you're getting REST APIs with a whole bunch of endpoints. In the serverless world, functions only have one. So it's almost like we've taken a microservice and we just sliced it into the component parts. Every single endpoint has been sliced into a separate piece, okay? So your applications in serverless world look like a collection of small functions, each of which has a name and some single function, right, that it does. Now this is kind of an advantage in the sense of, well, actually I'll get to the point here. The advantage is it's a little bit easier to think about one algorithm at a time. This is why we decompose problem into classes. We decompose classes into methods and functions, because we want to be able to focus on, 8 or 9 lines or 10 lines of code, 12 lines of code, right? Dealing mentally with tens of thousands of lines of code isn't as easy as dealing with a few. So if we can just chop our problems up into small ones, this is the promise, right? I don't know if it's, no one's proved this is totally solving the world's problems, and it's not, of course. But trying to break a problem into small pieces that we can solve individually and then combine them together to make solve complex problems. Right? So it's easier to think about that. It's easier for you to write a small method. It's easier for your colleagues to code review. It's easier to debug. Right? So these are the promises of making it easier. The scale is something I'll talk about in a minute, but the notion that you can scale these applications easily, transparently, is a major factor of why serverless is interesting for us. You can imagine if I have serverless functions that have input, output, and have no inter-process communication going on, any kind of coordination, I can scale that much more easily because they're single standalone units than I can if it's a much more complicated application. Of course, deploying small things is easier than deploying large things, so you can move fast. Netflix talks a lot about microservices, excuse me, microservices, about how they replace microservices all day. Right? All during the day, they're constantly replacing and upgrading new services. They have an active DevOps sort of life cycle at Netflix. And so that same notion applies for functions. If you deployed a set of functions, you can easily replace single units, single ones, over the course of a day, have a full sort of DevOps sort of life cycle, keep things working. Right? You can innovate faster. And one of the key attractions for a lot of companies is that in functions, you're typically only paying when they're used. So rather than if you deploy a microservice to some container platform and it's spun up, the clock begins, right? You're starting to pay for the compute you're using. That thing is listening on a port somewhere for some incoming request. In the serverless world, it's not listening. These functions are passive, they sit there. The infrastructure, the serverless platform, is doing the listening for you. it receives a request, it starts a function, so the clock starts on compute you're consuming, your resources you're consuming, the computation returns a result, the clock stops, and that's how much is paid for. And this is pretty universally the case. So what's nice is you can deploy lots of functions and pay nothing until they're used. It also is nice in that if you have functions that are infrequently used, you're not paying for deploying them, right? So you have a service you've deployed that is called once a week, once a month. It does some batch type work once a month for you. You're not paying for it being deployed, you're paying for when it runs. So that's a nice economic sort of argument for why this is attractive for companies. So I'm Canadian, I'm from Canada, so I use the hockey stick for my metaphor. But this is maybe the most interesting thing about functions, or FAS platforms in general. Okay, so let's say you deploy an application and it's an Instagram type filter. Okay, so let's say I have a function that takes an image as an input and puts puppy dog ears on it and returns you the new image. Okay, that's all it does. So I post this on my FAS platform and I tell my children at school, hey, this is a cute thing, you can try this with your friends. So their friends try it out and they're getting back cute puppy dog pictures of themselves. And so, it gets around the school, so it's getting popular. Okay, and then someone at some point posted on Reddit that there's this cool function, and suddenly the universe is calling me, okay, and it scales like crazy. Now, as a developer, am I concerned? Like, as the author of this code, do I have to do anything to make it survive this inflection point? Well, no, right? Because I built this thing, it has input, compute, does output. I can have 1,000 of them, I can have one of them, I don't care. Right? So as a developer, this is a nice world. I don't have to worry about scaling. As if I were a company deploying some service and I hit this inflection point, I can relax and know that the FAS platform will scale to handle the incoming workload. So you know that many companies that I'm familiar with in the large US retailers, they worry about this, right? So they have their Black Friday, which is their, or Cyber Monday, which is their Thanksgiving. Again, I'm not American, so I think it's November. But anyway, I won't go on about that. So they worry about this all day, right? Or all year. Like when November comes and everyone starts buying like their TVs, whatever, online, we're going to have this ridiculous curve. So what do? If they're in their own data center, they have to plan capacity to handle that one case. If they're running on a FAS platform, they're not worrying at all, right? They're building their systems to scale. They know that the platform is responsible for doing the inflection point sort of load handling, so they can relax. So this is the main. This really is the big thing, right? Scale, huge scale, without really having to deal with it yourself, to a degree, right? So where is serverless today? Well, there's good news and bad news, of course. So this is a great headline. Serverless is eating the stack, and people are freaking out. Lambda has stamped a big deprecated on containers. So containers are clearly dead, according to the article. This company is a training company, so they may have interest in selling you some new training. I'm just saying. This is a year ago. Serverless adoption on par with containers. Okay, so let's have a show of hands. Who's using containers, like development at least? Okay, that's pretty good. And who's using containers in production? Anyone? A few? Okay, and all of you are using functions in production now? No, okay. So this is a complete lie, apparently, but it sells newspapers. It's a good headline. This is a tweet from Chad Aramura, who a VP I work with on the serverless team, and he was talking to an analyst, and they said, quote, interest in serverless functions from our customers has ranged from astronomical to outrageous. So customers are freaking out. They are, I guess. This functions thing is so hot. What is it? They talk to Gartner, they talk to Forrester, they talk to all these companies saying, tell us all about serverless, it's so cool. And then they come to the people like Oracle and Amazon and so on and say, tell us about your serverless offerings. So this is a cycle here, right? It's going on. So we're in the hype cycle, right? So in the hype cycle, we're up there. It's exciting, right? It's the greatest thing ever. It's going to take over the world. Or apparently, according to the press, it has taken over the world. But this can't last. Right? It can't last. Soon we will slide down into the trough of disillusionment and realize that, or think that functions are terrible. We all tried them. They're the worst thing ever. We should never have used them. Bad idea. And then, like every technology, we learn how to use it properly, and it becomes something we can just incorporate into our bag of tricks. Right? So serverless functions are not a panacea. They don't replace anything. They're just something else that fits into your arsenal of technologies you can use to deliver systems for your customers. So, right now, don't buy the hype. It's just another technology, right? So, the question then is for Java. Where is Java in the serverless space? Maybe many of you have seen this before. This is the Red Monk language ratings review they do. Based on the bottom, it's got GitHub projects, and on the left-hand side, the y-axis is Stack Overflow questions. Okay, so you can look for your favorite language in there. Sadly, my favorite languages are sliding down, like down to the lower left, the cool old languages. But good news for Java, it's up there, right? So everyone's using Java. 14 million, I think, was the number I heard the other day. 14, 15 millions of people are using Java. So clearly, it's one of the top languages in the world being in use. Must be a great language for doing functions. Bad news is that's not true. Okay, so at least this is not scientific. This is from serverless.com. They build an open source CLI to help you deploy serverless applications to different platforms, trying to give you a unified experience. So they track the types of applications that people are deploying. According to them, about 75%, and this is the 2018 numbers, and I'm surprised because it's Java 8 here and an older node now. 75% of their applications being deployed are Node. A lot of Python in there, a little bit of Go, not so much Java, almost 5%. That's not that good. And the trend isn't very good either. So if you look at over the course of a few months, Python 6 is going up. 3 is going up as expected, while 2 goes down, so one replaces the other. Node, surprisingly, is sliding down, but Java's kind of level, right? So Java's not taking off in the serverless space right now, right? So why is that? This is the key question. Why is that happening, and what can we do about it? Right? We're Java people. We want to know. We want it to work. So the history of Java so far in serverless space is Lambda launched in 2014. They're the first in the market with a large commercial offering of FAS. And they added Java support a few months later. So it's been out there for 3 years, right? So this is the biggest player in the market. They've had Java 3 years, and yet those numbers we saw about deployment are also including people deploying to Lambda, Azure, and so on. So the question is, why are these other languages so popular? Like, what's up with Java, right? Is it because people who first adopted these functions are thinking, well, they're small little functions, they're good for like little scripts, and for scripts I use Node, or I use Python. That's my scripting language, so that's what I would use in this world. Bigger concerns are that the user experience of developing for functions with Java isn't necessarily as good as what they are getting in other languages, right? So that's a concern. And maybe the biggest concern is that the JVM is just not suited for this environment, right? A world where you're running small things for possibly short periods of time. And so that's not really what the JVM, the JDK have been building for, right, in the past. That hasn't been their focus. So maybe many of you read this article. This is James Governor. He wrote, "When web companies grow up, they turn into Java shops," right? So we have lots of stories of big players, Twitter and so on, who started with something else. Then when they had to scale, they went to Java. So the question for us is, or for me is, when function companies grow up, do they turn into Java shops? Because right now, those guys aren't in Java, right? They're in something else. So this is the challenge. So if we're going to have Java for serverless functions, I've written up a sort of criteria of what I think we need it to do, and I'll walk through and see how this is working for us, right? How things are going. But I think people want to just program in plain old Java. But people don't want some trimmed down Java that's like the micro Java for serverless. They just want to program in Java. They want to use the tools they want to use, right? So you can't tell someone, well, only this tool chain works for functions. It has to be whatever tool chain, or the tool chain they like, or at least a wide choice of tool chains. They want to build big applications. People are fine with, okay, the function is like this little thing, right? So I mentioned, it's really easy to think about input, output, but how do you build apps, like actual applications out of these things, right? How do you put them together? How do you build real things? So you want to be able to do that, and you want it to be fast, right? So the problem with the functions world is you make a call to the service, and somehow this function is spun up, does its job, and then exits, possibly exits. We want that initial call to be quick, so we want it low latency. And JVM isn't known for high boot time, fast boot time. So that's a challenge for Java also. So I'm going to talk about these problems somewhat in the context of FN. So I work on the FN project. I don't know if everyone's heard about it. It's open source, Apache 2. We're on GitHub. It runs anywhere. I'm going to run it on my laptop today. People have ported it to Raspberry Pis on ARM. It's got really good Java support. I'll talk about the Java support. So Java is obviously really key. I guess I work for Oracle, so Java is important. So we have excellent Java support. And just so you know, so our deployment model is we package functions as Docker images and deploy those and run containers. Okay, so in our world, in this FN world, functions are containers. And we aren't the only ones doing this. In fact, people like Kelsey Hightower, who's a Google advocate for and guru of the serverless world, agrees with us that containers are probably the right deployment unit for functions. What's nice about this is it's an open source project, so you can see how everything works. So we don't hide. We use Docker. We don't hide Docker. So if you're a Docker person, this will look comfortable for you. If you're not a Docker person, you don't have to see Docker. You can kind of ignore it. But it's a critical component because we're going to talk about Java and Docker. So I'll start off with talking a little bit about FN with Java. And what I'm going to do is just tell you what we have for support. So we have this thing called an FDK, a function developer kit. We have them for Java, for Node, for Python, Go, and Ruby. We have a library, so there's some API that you can plug your function into and say, here, run my function. I'll show you this code in a second here. We have JUnit support. So this is really important, right? If you're a developer, you want JUnit support. That should be there out of the box. And then we have some Docker builds, Docker images for building and for running. So I can actually build Java applications on my laptop without actually having Java installed, because the whole build takes place in a container, and then the runtime is produced as another container. So it's all Docker. I need Docker, but that's all. Okay, let me just go show you code, because that's more interesting. Okay. Okay, well, clear again. Okay, so I am going to create a new function. We have a little utility, command line utility called FN. I'm going to make it a bit bigger. So FN does a bunch of stuff, right? We can do all kinds of things. But what I'm going to do, I'll try and jump to the top here for you, for the back. So if I go FN init, okay, now I'm typing standing up. So if I make a mistake, like please pair program with me and tell me, no, you missed a bracket or something. That happens, right? Runtime is Java. I'll make a function called hello. Okay, so we generated some boilerplate. You don't have to use this, but it's nice to have a little bootstrap, right? We put functions. If I have a function called hello, we put it in a folder called hello. So you can organize your functions by convention, putting them in folders of the same name. Okay, so let me show you what I've got here. Okay, so that's what I produced. This looks very boring, right? This looks like a standard POM, Maven-based application. I've got a POM file there. I've got a function class. I've got a test class. And I have one more file, a func YAML file, which is the metadata we use for functions. So I'm going to go in and show you what this looks like. Now, let's see here. Come on. Code is here somewhere. Yes? That's very strange. Okay. So let me show you what that looks like. Okay, so here's a Java function. If I make it a bit bigger, it won't quite feast. It just about fits. Okay, so this is amazingly boring looking Java. Okay, so I'm proud that this is boring. This is the whole idea, right? So I don't want you to have to learn something new to use Java. Java should just work as a function without much change. I've got a function or a class called hello function, and I have a single method here. I could have more than one, but this method is my entry point, right? That's my one entry point to this class that is the function. It just does hello world. If you pass in a parameter, it returns hello whatever, or hello world. It takes a string, returns a string, right? Nothing very strange about this, simple function. I can show you a test for that function. So we have full JUnit support for this. So I can get a testing rule. I can create an invocation of that function. I can then actually run that function itself. I can go and get the result. There's a large API here for passing results, passing parameters in, no parameters, and whatever. Check the single result and then do some asserts. So this is standard stuff. I'm here in code. I can hit run this test. Okay, so it passes. So my code's working. So here I am doing function development. It looks like Java, nothing fancy. I'm using these tools. It's Maven, JUnit. It's pretty vanilla, right? Which is, again, kind of the point. Oh, and I'll show you one more thing. I'll show you the metadata file. There's not a lot going on here. Just it tells us the name of the function. It's Java. It does tell us the entry point. So as I said, the function class and method name are not important. You can declare them, call them anything, put them in here. No special names. So that's all we have. So I can do fn run. Actually, let me put verbose on here. So verbose mode. Verbose mode so you can see what happens. So you see, if you're familiar with Docker, you're seeing some Docker stuff going by, because we actually are using Docker under the covers. We're actually behind the scenes generating a Docker file, running that Docker file to take the code, run Maven, package it, and produce an output. So if I do a Docker images, okay, so here's my image, right? So I actually have produced a Docker image. And you saw I did run, so again, if I do fn run, right, it runs, produces the output. If I do something like echo Dresden, right? So fine, right? So I have this little function, right? That's pretty easy to do. Now, what you saw there was, you saw in the command line, I just catted, I just sent some stuff to standard input, and that standard input somehow got into that method, right? Somehow, through the function developer kit support, oh, that's the test. Somehow that input I provided got into this string. So string is default. It's very easy to do, right? Anything that comes on standard input or is passed as a payload gets passed to the function. But you're not limited to simple types. Let me pop over to one I prepared. It's like a cooking show. I have something in the oven. Okay, so this is almost the same. This is almost exactly the same. A little bit different, just to show you a little bit different. So this function takes an object, takes a POJO, right? So I have an input object, I have a result object, it takes a POJO. So what's happening here is if you pass in this case, JSON, we will automatically unmarshal the JSON into this input POJO, pass it in as input, get the result object, and then unmarshal it back into JSON, or marshal it into JSON and pass it back out. So we have automatic support for complex types. You can control this. It's using Jackson. You can control the Jackson annotations. You can add some annotations to customize the mappings. You can also swap in whatever you want. So if you don't like Jackson or you don't like JSON at all, you can use XML, your own proprietary format. It's completely pluggable. But the idea being that the FDK is taking care of whatever's coming in on the input and getting it into your code, right? So you want to get it into your code. It's not something you want to be fussing with in the functions world. Like, how do I get my input? How do I connect things together? It simply just goes to my function. Okay, so let me go back over to the slides here. Okay. So I think you saw plain, boring Java code, right? Yay, boring. And I was using just some tools. I could use Eclipse. I could use anything that supports Maven in this case I could use. Today, the FN has support for Maven, but Gradle should be no problem. It's a bunch of Docker containers that do something, right? So we have a nice pluggable architecture. We just use a bunch of Docker containers to do parts of our flow. So that seems straightforward. Okay, so Java looks pretty good for building basic functions. That doesn't seem too hard. What about building complex applications? This is where things are interesting. So the functions world is pretty much at this point of having to figure out how do we build applications. So we've come up with something called FN Flow. Azure has a thing called durable functions, which is similar enough, actually fairly similar to what we're doing in philosophy. IBM has some experimental things in IBM Labs called Composer, which is more of a visual to draw pictures and try and describe the workflow. So we have Flow. And our philosophy is a little bit different than certainly IBM's. So I'm going to show you a little example here, walk through. I have an application that's going to do some plate recognition. Perhaps I'm the police, okay, and I'm looking for a stolen car. So I'm going to have like cameras watching streets, and they go by, and I'm going to snap some pictures of cars and look for the stolen car. I know the plate. Okay, so what we do in this example is we go to Flickr and we find some pictures of cars that have license plates, hopefully. We have a function that looks for the license plate in the image and gives us back the license plate, and it gives us back the coordinates in that image of where the license plate is. And I have another function that will draw, this, like you see here in the picture, a little yellow box around the license plate so I can sort of call it out and see it. And then after that, I'm going to post to Slack and Twitter, right? Or I could send it to the police alert line, I guess. This is all on GitHub, so this code's available on GitHub. It's not all Java. You'll see that actually a lot of the functions are actually there's Ruby in there. It's like a very polyglot, but Java is actually the control. I'm going to show you that part. So Flow is designed to build these highly scalable applications, right, with just functions. And our goal is to let you describe your algorithm in code, basically write Java code that just describes the algorithms, right? Why would you have to go and use, like in other technologies, they want you to write YAML files. Like if you're a developer who knows Java, why would you switch to YAML to try and compose things together? It seems to us counterintuitive. Java has great semantics for writing algorithms, obviously, so we should use that. And something that's more subtle about what we're going to do here, when I compose together functions, I'm actually writing a distributed application. Because these functions are running somewhere in a compute fabric, right? The FAS platform is just spinning up functions on available compute. So you're actually inherently doing distributed computing. And in doing so, you kind of need some control, or a little bit of control over sort of my fan out, fan in, synchronizing things together, and we have support for that. Who knows completable features? Anyone using completable features? A few? Okay, it's been there since 2008. It's a framework designed for, it's a feature framework, it's for features, to let you, in the case of completable features in JDK, is for managing multiple threads. So you can create a piece of, create an action that creates a thread, compute something, and you can get a handle to that result. So you can get a handle saying, this is the result of some computation. I can get the handle for the result, even if it's incomplete. I can pass that result around. At some point, it'll resolve to a value, and I can use it. Features are really old technology. I was doing them a long time ago. It's nice that they're in Java, but no one knows about them very much for whatever reason. It's in Java util concurrent, right? It uses the fork join pool. So it's a nice API. The problem is it's designed for threads. So we worked with Brian Getz and the Java platform team to basically, I guess, provide an implementation of completable feature that runs for functions that runs across compute fabric. So the processes are running external to the JVM, so multiple JVMs. So this is what we've done with Flow. So here's the application I'm going to build. I've got a function called the scraper. It gets the images out of Flickr. I've got the place detection function. I've got the draw function that draws the little box on it. And then I got a couple of functions to post to Twitter and to Slack. And I can use completable feature API to compose together, or to structure the algorithm. So I use then compose to sequence. I can use all of, as you see here, to say I want to do all of these things. And I can even do, say, when complete. So when all these tasks are done, I can basically synchronize and join back and then do some action. So I have very nice primitives for doing distributed computing that I can use for my functions. And so that algorithm gets put into a function. So we have a function, we call it the flow function. It just is, this is the algorithm. I've got these floating functions I can use. I just write an algorithm, go here, go here, go here, and that's a piece of code. So here's that code. Now, how good is that? Oh, it's not very good for you back there, I think. I don't think the color is so good. That's too bad. Okay, so I actually have a mouse. I have a mouse. Okay, so I'm just basically going invoke a function scraper. Then I'm saying take the results, and I'm going to invoke detect plates. Oh, I'm looking at my machine and moving over here. Detect the plates, then compose. I invoke the draw function. I have all of. Take the current flow, all of these functions, and then finally, when complete, come here if it's successful or not. So if you're using completable feature, this looks very familiar, except that the workloads are no longer inside the JVM. They're somewhere in your compute fabric. So we've built to understand what's happening at runtime, because that's the challenge when you're working with these kinds of environments. We have this experimental UI for Flow, and each of those bubbles is a function. Okay, so the very first function at the top left, little bubble, is that one, the algorithm you saw. It was invoked. It calls the scraper, which is, where's my mouse gone again? It calls the scraper up here. I think that's right. And then you'll see here, it fanned out. So all those images, each image we got out of Flickr, we invoked a detect plates function. We actually, 100 or whatever it is, we decided to maximize, to limit that at. We've called a whole bunch of functions running concurrently. Once the detection is completed, the pink one you see here on the right is then the draw and so on. So you can sort of visualize what's happening in your algorithm, right? So how is this working in real time? So we can plug right into the Flow server, the piece that's actually orchestrating this, and take a look. The cool thing with this is you can click on the bubbles, and you can look at the stack trace. So you can look at the Java. If there's a problem and it's failed, you can look at the Java stack trace. You can click on a bubble and see, how did I get here? What's my path? So we've been working very hard on making this practical. There's one more cool thing that Flow can do with Java Lambda. So here's an algorithm that just takes an integer, doubles it, returns a string, okay? But with using Flow, these lambdas, it turns out, can be treated like functions, like actual, like FAS functions. I can take these lambdas. It turns out lambdas can be serializable, if you didn't know. So we can take these functions here, serialize them, and actually run them on independent nodes. Right? They become true functions in the FAS world. So it's a very natural way for you to be able to decompose your application into a bunch of functions, leveraging a lot of concurrent compute abilities with just Java Lambda. So it's a really cool feature. It's completely natural for Java programmers. So we think this idiomatic, natural, using Java to build large applications makes sense. I'm not convinced that writing in YAML is going to be as effective as this, for sure. So that's, I think you can build complex applications. So we're doing quite well on my checklist. The last one's actually a bit of a hard one. So we're running Java in container, right, which is common case. So containerized Java has a few challenges. One of them is to respect the constraints of the container it's in. If you know right now, or in the past, if you ask, the JVM has a number of APIs for examining its runtime environment, and they have in the past returned the wrong answer. So if you ask how many processors you have, how much RAM you have, you can be getting answers about the host rather than the container, which leads to bad things like bad size thread pools, out of memory, all kinds of bad things. That's a challenge. We want them to start really fast. Okay, so again, there's latency. When I invoke a function, I want a result, right? I don't want to wait a second for this thing to spin up. And I want small images, Docker images, and I'll explain why that's important, but it's actually quite critically important also. So there's a lot of work in the JDK. So OpenJDK has a lot of bugs and JEPs running to address this in-container use case. So things like making sure commands work that interact with Java, the JVM, in container. The last one there, the second to last one, the JDK 8203357, wow, they have long numbers. That's a lot of bugs. Is container metrics. So this is actually it was replacing another one where they're adding API into the JVM to let it go off and get actual correct answers about the container environment. So you can size your application correctly when you're running. That's coming in 11.01. The last one's one that just came out in 11. This one's intriguing. It's no garbage collection. You can have a no-op garbage collector. So imagine you have a very short-lived program. Why would I want to spin up like a garbage collector? I run for 500 milliseconds and I'm dead. Why am I wasting cycles on garbage collection? So this has been added here for those kinds of reasons. And I have to give the JDK team a lot of credit. I've been working with them now for, I think, about 3 years on this notion of Java in container. And we've had lots of conversations about what's possible, what's not possible. This was one of the possibilities, and they've gone ahead and done it. Right now it's release code. So this might be useful in some cases, not in others, but they're giving you options, right? So the JVM is growing up, right, to be a container-compatible technology, if I can put it that way. So that's really good news. On the startup time, there's a few techniques. Anyone using class data sharing? One or two people. Okay, it's like, apparently this has been in there since 2004. Class data sharing lets you take the JDK classes that are part of your JVM and pre-parse them. So every time you boot the JVM, it reads the bytecodes and builds in-memory structures for those classes. Every time. So, if you're doing it every time, it's obviously wasting a lot of time. Why don't you do it once? So class data sharing lets you take your JVM, tell it, hey, parse those bytecode files and dump an archive, essentially. So you can actually have these classes pre-parsed. It boots faster. Application CDS does the same thing for your classes. You can have the JVM read your application classes and basically pre-parse. So you're basically moving part of the later work earlier, right? So I'm moving stuff to build time. I'm moving the parsing. I'm moving all kinds of things that cost me startup time to build time, which is kind of the goal. The last one, AOT compilation, which is experimental, lets you compile your classes to a shared library. So it does native code compilation of your classes and produces a .so file, which you can then link to your JVM. So this is what Hotspot does after so many times you go through executing it goes through your code. hotspot goes, wow, that should really be native code, and optimizes it down to native code and uses it. This AOT option lets you do it ahead of time, saying, I really know that code's going to get run. Please compile it now and link it. So that's a really nice feature, and I'll talk about that again in a second here, because this is an experimental feature, but there is some more code in the Graal project, which you may have heard of, that is making this a bit more easy to use, or same technology. So on the small container images, this is a key thing. Again, imagine my FAS world. I have these computers all spread out, ready to run functions for me, and someone makes a request to my service, and I need to spin up a function on a given node. And I have to, if I'm in a container world, if I'm using Docker, I have to get the Docker image over to that machine. I have to transfer it. So a small image is fast to transfer. A 400 megabyte image, as we saw there for Java, that default one, that's going to take a while. So again, it's going to hurt me. I want fast response, so I need small images, just for Docker's, just for data transfer's sake. The other two, the cache on write, or the copy on write caches and the overlay FS, these are just setup things that Docker has to do when it boots a container. So it just does its own bookkeeping and setup. Turns out small images with few layers, if you know Docker, are faster to boot than large, complicated images, lots of layers. So you want fewer layers, small images. This is our goal for the JVM. So how do we do that? Well, we have a couple of options. JLink is there. JLink for removing classes you don't need. Anyone using JLink? Oh, they're going to be so disappointed back there. Okay, I won't tell them. The JDK's got like 500 and something meg of classes, but for the like the middle there, and the Netty needs about 60 meg of classes to actually run. So you don't need 500, half a gig of classes you're using in your application you do not need, right? For example. So using JLink is good to shrink your application down. Definitely a good thing. Even works without modules. Smaller images. So there's a project at OpenJDK called Project Portola. Their goal is to get the JDK running on Alpine Linux with Muscle for the C library. And the reason it's considered a port because there's a different library, right? So the JVM is built with, I think, libc. You know what I mean? And so this is a different library, so they're having to do a port. But this is a very small world, right? So we just want enough operating system to run the JVM. That's all we care about. We don't need all the other stuff. So this is a nice project at OpenJDK for solving this problem. So small image again. And then the last technique that I want to talk about here is Graal. So who's heard about Graal lately? A few. Okay, well there's a talk today, I think in the next session on Graal. So after you see this, maybe you'll be intrigued and go listen to that session. The Graal team, actually, a lot of them are in Germany. And so this came out relatively recently. They've been in Oracle Labs for a number of years building products and developing this technology. But it gives the ability to do full ahead-of-time compilation of your entire application. Right? So I can take a Java application, I can compile it like a C code or a Golang application into just a binary. So essentially, it's a binary with your code and a garbage collector. Right? That's kind of what you get when you run through Graal. Also, because it's compiling ahead of time, it doesn't have any of the overhead of hotspot. It eliminates 2 of the 3 sort of memory usages. It removes code caches, removes something else. But it's much smaller memory consumption. So this is all good stuff. So why don't I just show you what it looks like, what Graal looks like. And I think you'll be surprised, because it's so straightforward, actually, why you'll be surprised. So I'm going to, I've got a script here to start this, because the command is long. So fn init image, blah, 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 native, hello SVM. So I have a function called hello SVM. I just created that. Now, full disclosure, I'm showing you a pull request. So this is really bleeding edge. So the Graal integration into FN is happening now. So on Monday, we had a pull request. I've got the pull request. This is like the latest, hottest stuff. And so far, it's working just great. So, sorry, wrong one. All right, so I'll bring it up in code. So this is this is the Graal version of the hello world. It looks exactly the same, which is good, right? So this is just, I want to take that same Java program now and I want to do ahead of time compilation. So I have a little function, same thing. The only thing that happens that's different with Graal is doing ahead-of-time compilation. So it essentially walks your call chain, right? So it looks at your classes and then figures out what you need transitively, does a transitive closure, and includes those classes. Since the FDK invokes your function with reflection, we need to tell Graal, the compiler, or the native code compiler, that you have this class that you need included. So they have a configuration file, reflection JSON, that says, hey, that class has to be included in the binary. That's pretty straightforward. And one thing they do that's different too is, I told you we use Docker in FN. You can use it yourself explicitly. We kind of do it magically behind the scenes. And so you can actually write a Docker file and give us a Docker file for FN to build your project. And in our func YAML file, you just say the runtime is Docker. And we go, oh, OK, you're telling us it's Docker, we'll look for a Docker file and we'll do a build. So so the integration is based on just writing a Docker file. And you see here, if I try and squeeze this off here, they do a normal Docker build or Maven build up top. So it's Maven package. Then they run the native image. They basically run a processor. They take your jar and they compile it down to a binary. And then they package it up. They're packaging it right now in a Scratch. I think that's changed. This is a very small image, or a low overhead image, right? It's basically just minimal OS and this binary. So if I run this, and actually I know from history that Docker is very clever and it caches layers and does all kinds of things. It defeats demos. So I'm going to just change the code to force it to build. OK, so if I do fn build, I'll do verbose. OK, so running Docker build. That did not do what I wanted to do. Let's try and change this code here. So I just want to show you this thing running. Now, the bad news is when it runs, it takes a little while because native code compilation does take a while. OK, here we go. So it's running the Maven build. OK, that's all good. Tests are good. And then you see it's running the native image compilation here. So it's walking through the code references, all your code, right? So it's transitive closure of your entry point, in which our case is actually a reflection, so we have to tell it. So now the upside of this is, the downside of this is you pay a lot up front, right? So I wanted to move the compilation up front. As a developer, I'm now waiting for this thing. I'm thinking that you saw that it was the same code. I'm thinking that going in the future, we might see ourselves working with the JDK, hotspot, interactively developing in our debuggers. And at some point, we decide, OK, we're going to lock it down and deploy, in which case Graal comes into play, right? Package this thing for production, make it small, make it fast. It's the last thing I would do in my well, I unit test that too. But I would move this probably to later in the dev cycle. OK, so I did that. It built an image, Docker images, VM. Oh, SVM is substrate VM, so it's one of the pieces of Graal. So this image is 14 meg, OK? So I've got a full Docker image, the exact same code. Yeah, 14. Now, that's really impressive. So let me just deploy this code. So I have an FN server here I'm going to start. So here's FN running on my laptop. OK. I'm going to deploy the hello SVM here. I need, let's see here, we'll just say JUG for now to be short. I have an application. I need to group my functions into applications. It's a namespace. And local says I'm working locally here. Oh, yes. FN would be good, too. Your pair programming is not working. It's like, OK, so it deployed an application. And let me go over back to the hello world there and deploy that one, too. OK, so now I've got FN list apps. I have one app called JUG, OK? And then I have the functions of the JUG app. There's two functions there. So right now, the world is cold, right? There's nothing running it anywhere. So I'm going to run the hello world. I'm going to time it. FN invoke the JUG application hello. OK, so we're going to time how long that takes. So I call it 1.4 seconds. That's actually pretty bad. I call it again. It's really faster now. So FN is doing some clever caching, but it started up a container. That first time we saw the call was quite expensive because the JVM, the container had to boot, the JVM had to boot, the program got control. It takes a while. So if I do the same thing now with the Graal, now This is not scientific because it's running a non-real workload on my laptop, but at least we'll see something here. Actually, we'll do this one. So I'll call the graal function. We'll time the first invocation. Oh, that's quite fast. 600 milliseconds versus 1.4 seconds. If I call it again, of course, it's fast because it's actually already running again, right? But this number here is the key one. What does it take to boot this app? It took almost a third, one third of the time only, compared to that 400 megabyte image. So I'm really seeing benefit from graal. If this is at scale, this is going to really add up. If I have customers invoking functions, they want quick response, low latency, the ahead of time compile with graal is really helpful. All right. No, this button. So I think that, for me, I think I've convinced myself, anyway, I could use Java to do functions. It looks pretty easy to do. I can use whatever tools I want to use. I have a framework for building complicated applications, and there are tools in the JVM. So I've got things like just JLink even, right? All kinds of things I can use as a Java programmer to make my applications boot fast in the functions world, which is a critical thing. And again, if you think about the adoption of Java, Node, Python, they boot pretty fast, right? So this sort of script in the cloud. But when I'm using something like graal, I have something that's just as fast, right? Certainly as fast. So really, serverless Java right now, 5% maybe. Are we going anywhere? Does it have a future? I think absolutely. I think that the technologies that are out there, that are appearing, the ongoing work means that if you're looking at future functions in your future, that Java is a viable choice for you. You don't have to go to Node. You don't have to go to Python. Why would you go to Python? Anyway, that's just me. Okay, well, thank you very much for your time. I hope that was interesting for you. Thank you.